Okay. Exam 2 is a week from today. No, we do them on Monday, isn't it? So it's Monday. I'm sorry. Next Monday. What? 2 more days. What?
Wednesday and Friday. And the test.
Oh yeah. Exactly. That sounds right, doesn't it? Maybe I should check. Syllabus. Okay, exam 2, March 24th. Yes. Okay. So it's next Monday, and the topics will be, remember, these tests are all cumulative, so you need to be ready for the old stuff too. So everything up through rigid body kinetics. Okay. Anybody have any questions about the test? Yep.
Is there gonna be like a bias though for the newer stuff?
Oh, that's a good question. I mean, yes, I suppose. I mean, there will definitely be a rigid body kinetics question, you know. Yeah, but the way to, I mean, the way I think of it is like, as we go through stuff, you have to understand everything, and then basically just go back to the beginning, look at the daily homework problems, ask yourself if you know how to do it. If you do, go on to the next one and just work your way through. I just want you to keep refreshing your memory about all of the old topics. Okay. It's sort of a pain now, but it makes the process a lot less painless at the end when you have to get ready for the final. So that's the small trade-off.
You mean everything, so even before exam 1?
Exactly. And that's true of all the quizzes and everything too. Any other questions? But yeah, like I'd never have given a test where like I just didn't give any new stuff on it. So in that sense, there's a bias towards the new stuff. But okay. Any homework questions anybody want me to go over? Yeah.
14.
Okay. This is kinetics, rigid body kinetics.
Could you also go on number 15?
Yeah.
These set up equations.
Sure. Okay, so 14. So this is a rigid body problem. We're just going to go through the steps. So step 1, does it have a fixed point? Yes. And so the about point is the hinge. Step 2, we have to calculate the mass moment of inertia of this thing. Now, the mass moment of inertia does, for something in the plane, does not depend on its orientation. Okay, so you can think of it like we're going to calculate the mass moment of inertia of this thing. And we have to calculate that mass moment of inertia about the point, around the about point. Okay, so we can do that as we'll calculate the mass moment of inertia of the big outer rectangle. And then we'll subtract it for that circle. Okay, so for the outer rectangle, the mass moment of inertia about the center of mass is 1/12 times the total mass. Okay, now this thing is 50 kilograms. But so we're not quite ready for this yet. So, well, how do we know what the mass is of that big outer rectangle? Well, we can assume that the ratios of the masses are the ratios of the areas. Okay, so the area of the outer rectangle is 2 times 0.7, so 1.4 meters squared. Okay, the area of the circle is that as a radius. Okay, that should be a diameter, yeah. Otherwise, this doesn't make any sense. So it has a diameter of 0.5. So the area is pi times 0.25 squared.
0.196.
What?
0.196.
Okay, 0.196. And so what we know is that the total rectangle, okay, so the total area is 1.4 minus 0.196. So 7.143.
No.
That doesn't make any sense. 1.4 minus 0.196. 1.204. Okay, so we know that the ratio of A total over, well, let's go A. Yeah, sure, it works either way. A total over A1 is equal to the total mass over the mass of body 1. And so 1.204 over 1.4 is equal to 50 over M1. And so M1 is equal to 58.139, let's just call it 0.14. Okay, and then that tells us that the mass of the second one is 8.14. Okay, so now we have the masses. So now we can say that the mass moment of inertia of 1 about its center of mass. Everyone with me on what I've done so far? So this is equal to 1/12 times the mass of piece 1 times the quantity 1.4, is that what it was? No, 2 squared plus 0.7 squared.
Okay, so ICOM is the equation for the rectangle. Is that going to be given on the formula sheet or?
Yeah.
Okay.
And so I get 21.75 kilogram meters squared for this about its center of mass. Question?
Don't you have to do the plus MD squared?
Yes.
Okay.
Okay, so this is the moment of inertia of the rectangle about the rectangle's center of mass.
Oh, gotcha.
And so now we're going to go the moment of inertia of the rectangle about the hinge or around our about point is 21.75 plus the mass 58.14 times the distance from the center of mass of the rectangle to the hinge. So that is 1 squared plus 0.35 squared. So that is 87.02. Okay? With me on that? And now we can go to body 2. We already have the mass for that. This is, so the moment of inertia of that circle about its center of mass is 1/2 times the mass of that shape times the radius squared. So that's 0.25 squared. And so I get 0.254. And now parallel axis theorem to get it about the hinge. So we have 0.254 plus 8.14 times the distance from the center of mass to the edge. Okay, so vertically, that distance is going to be just half of the width of the rectangle, so 0.35. We're going to square that. Horizontally, it's going to be 0.35 plus another, so the diameter is,
Center should be the same distance from the top edge as the right edge.
the center should be, okay, let's see. So this is, so what's this distance here? This is 0.1.
Should just be negative 0.35, negative 0.35.
Okay. Point 0.35. And so you end up with 2.25 about. So the parallel axis theorem part in this case is a bigger contribution than the moment of inertia about the center. That happens pretty often. And so now finally, the total moment of inertia is 87.02 minus 2.25. So 84.77. Okay. Any questions about that? Well, that was step 2. There's still one more thing we're going to have to deal with, and that is, so the next step is the free body diagram, and the last sort of tricky thing that we have to deal with in this problem comes up when we draw the free body diagram. So we have an object like this. There's an unknown force applied to the object by the hinge. And the only other force we have, the only other load we have, oh, that's not true. There's an external couple of 100 Newton meters. So it doesn't matter where you draw that. I'll just put that in here like this.
Can you draw the hole with the free body? Technically, I guess it's a.
Yeah, I don't know. Yeah, that's a good question. I'd say so. But it does sort of clutter the problem. But now we have to put the weight in. And now you ask yourself where the weight goes. And that brings up the last thing we're going to have to calculate is we're going to have to calculate the centroid location to figure out the row vector for the weight force. But it's going to be somewhere shifted over this way. And it's going to be the total mass. So I'll write this as M total times G. Okay. We might as well calculate the centroid now. This is at an angle of 20 degrees. So what's the easiest way to do that? I think I'm going to just calculate how far, like we know there's an axis of symmetry, a line of symmetry here. Okay, so I'm just going to figure out how far it is along that line of symmetry, and then we'll do the trigonometry to come up with the components.
Can't we just put the axis? Or critical system?
Yeah, we could do that. What would that mess up? That would just mess up the weight force. So that's another way to do it. Yeah, for sure you could do that. Well, I already drew my components of this R vector in this coordinate system, so there's nothing I can do. Okay, so step 4. Well, let's do the centroid first. So I'm again going to do body 1 and body 2. And I'm just going to figure out the x centroid. So I just want to figure out this, you can. So I just want to figure out this distance d. Okay, so for body 1, the area is 1.4. We already figured that out. And the centroid of body 1 so I'm going to think of this as like a, well, it's just going to come out negative. That's pretty easy to deal with. But so I'm going to call this, this is going to be -1 because the whole length is 2. And then for body 2, the area is 0.196. And the distance is, that must be -0.35. And a total, we figured out before, is 1.204. And so that d total is 1 over 1.204 times 1.4 times -1, and then minus 0.196 times -0.35. And we get -1.11 meters. Okay, so this D total that we're looking for, well, I'll leave that off there. But that's how far we have to go. And so now, what's that as a vector, from R? So we have to go, so let's think of this as, yeah, right, so I'm gonna have to rotate it now. So yeah, maybe the way to go here is to use a rotated coordinate system, then all we have to deal with is rotating the weight force. Okay, so I'm going to use a rotated coordinate system. So then the weight force, M total times G as a vector is the total mass of this thing, which is 50, times 9.81, so 490.5, times the sine of 20, and then the negative cosine of 20. So 167.76, negative 460.92. Okay? So now we can go to step 4, do this table. This is a sort of sneaky, complicated problem. There's just a lot of steps to it. You look at it and it doesn't look that horrible, but the combination of having to calculate this combined moment of inertia and this combined centroid and then deal with the rotation, it's just a lot of going back and forth between things. Okay, so the first one, I'll do R. The row vector is 0 for that. The force is Rx, Ry. Moment is 0. Next, I'll do the couple. We don't care about these for a couple. And it is positive, right? Yeah. And the rotated coordinate system doesn't change anything about the couple because that's a vector in the z direction. We're rotating our coordinate system about the z-axis, so that doesn't change anything. So this is just 100. And now the last one, the weight. Okay, what's the row vector? Well, we have to go in Rx direction, negative 1.11. And then in our Y direction, we're going from the about point to the centroid, which is just negative 0.35. And the force vector is 167.76, negative 460.92. And cross product, it's easiest to do this on a calculator. You get positive 570.34. Okay, so step 5. Does this have a fixed point? Yes, so we don't need to use Newton's second law.
No need.
Yeah, and so then we're on to step 6, the moment equation. And now what we have is 100 plus 570.34 is equal to 84.77 times alpha. And so now alpha is 7.91 radians per second squared. And if you want to write this as a vector, that means this is 0, 0, 7.91. Okay, now I haven't really thought at all about what the question asks for yet. What are the accelerations of the four corners? So let's just do one of the corners. Let's do the acceleration of this one, and I'm going to keep this rotated coordinate system. You wouldn't have to. You could now. This angular acceleration wouldn't change as you rotated the coordinate system. So if you wanted to go back to like a standard coordinate system, you could. But I think it's going to be easier. The geometry is just going to be easier in that rotated coordinate system. So I'm going to calculate the acceleration of the green corner. Well, every point on this body is in circular motion around that hinge. So this is just going to be the acceleration of that point is going to be the watermelon equation. All ripe watermelons will rot. Our alpha, we went through all those steps just to calculate alpha. That's 0, 0, 7.91. Our omega, that's something that you can't calculate from the rigid body analysis, but that is given in this problem, -8. And that also is independent of the coordinate system we use because that's a z component. So 0, 0, -8. And then the r vector, the definition of that r vector is from the center of your circular spherical motion to the point you care about. So that is -2 for x, -0.7 for y, 0 for z. And now we can plug this stuff in. The acceleration is 0, 0, 7.91 crossed with -2, -0.70 plus 0, 0, -8 crossed with 0, 0, -8 cross -2, -0.70 is 133.54 28.98, and then obviously it should be 0 for z. There's no acceleration out of the plane. This is in that rotated coordinate system. So what if you wanted to express this now in our standard coordinate system, or if I wanted to compare my answer to people who did it in the non-rotated coordinate system? So I'm starting with a vector in this coordinate system. So I want to rotate my coordinate system from this to this. That's a counterclockwise rotation.
Makes it possible.
Positive, exactly. So it's a 20-degree rotation about Z. So my rotation matrix, I think when I brought this up before, I just did this in 2 dimensions. I think so in this class. So, so this is going to be cosine of 20, sine of 20, negative sine of 20, cosine of 20. And if you multiply, punch that into your calculator, you get 0.94, 0.342, negative 0.342, 0.94. And so the acceleration in the in the non-rotated coordinate system, or I guess let me just write that in the new coordinate system, is this matrix. Times our original acceleration vector, 133.54, 28.98. And I got 135.44, negative 18.43 meters per second squared. And this is in our usual coordinate system. Whew. You have to do that still for 3 more corners, but that's the easy part. Any questions about that?
For rotating the angle of your coordinate system,
Yeah.
would you also look at it as the vector being the hypotenuse of the triangle and then just adding degrees to the angle?
When you're doing what? So if you're not, so if you wanted to use
When
the,
you're doing rotating coordinates.
like in the last step?
Yeah.
Okay. Could you think of what? Once you're used to using rotation matrices, you have it programs in your calculator or whatever, it's just so stunningly much faster to just punch it in than to think like, okay, this is the sine, this is the cosine, multiply by this length, Okay, any other questions? Oh my gosh. Class is almost over.
Well, this is not related.
Yeah.
To, this problem itself,
Yeah.
but me doing the rocket challenge, we're doing some
Yeah.
trace right now for our prototype.
Yeah.
How would I phrase it? We are facing track as an issue because we're adding fins.
Yeah.
How can we solve this piece of eccentric?
Okay, well, so do you know, so you're trying to figure out like kind of the moment, because you're trying to figure out how it's turning, and you're trying to figure out like sort of the moment applied by the,
Yes.
okay. Okay, everybody, we have to wait on number 15, okay? This is important. We'll work on number 15 on Friday. Okay, this is the Rocket Club.
Does that mean we don't have to turn it in tonight?
Oh, is it due today?
Yeah.
Okay, we'll do the rocket on Friday. Okay? Yeah. Okay, number 15. Because the rocket, but in any serious engineering school, the Rocket Club comes first.
Wait, what? That's the actually.
What?
And
Iowa State, the Rocket Club came first. That's facts.
Yeah, exactly. See?
At least in the aero department.
Yeah. Yeah, in mechanical, it might be the solar car competition or something, but to us, it's the Rocket Club. Okay. Okay, well, 20 degrees. That's even, I mean, we did this on Monday. We just don't know the moment of inertia of the hollow thing, right?
You sort of missed half of that class. So.
Oh, okay. Okay. Well,
Did you post?
the notes, there's no video, but there are notes for it. But let's figure out the moment of inertia of that. Okay, so we have,
Yeah, you're right. We don't have the moment of inertia equation for a hollow disk.
right. Okay, so so is there let's think through the steps. Is there a fixed point? No, there almost is. Because the velocity at the contact point is 0, but the acceleration at the contact point is not 0. So there's no fixed point. So the about point is the center of mass. And now we have to think about the moment of inertia of this thing. And we can think of it as the moment of inertia of the outer thing minus the moment of inertia of the inner thing. Okay? What does it give? It doesn't give a mass. So, what? Oh, 1 kilogram, okay. So we're going to have to go through kind of the same procedure that we just did in that last problem. So the mass total is 1 kilogram. The mass of 1 over the mass total is, so let's calculate these areas. The area of 1 is pi times the radius, the outer radius squared, so 0.1. Yeah. And so that is 0.0314. And now the area of the inner one is pi times 0.08 squared. Pi times 0.08 squared. So that's 0.0201. And so the total area is A1 minus A2. So 0.0113. And now the total mass is 1 kilogram. And this ratio has to be equal to the ratio of 0.0314 over 0.0113. And so M1 is equal to 2.78 kilograms. And that says that the mass of the removed thing is so we want, yeah, 1.78. Okay, so now we can do the moments of inertia of the two parts. So for body one, and the nice thing here is we're not going to have to use parallel axis theorem. The center of mass of each of those two circles is the same as the center of mass for the whole thing, and it's the same as the about point for the problem. So the moment of inertia for one is 1/2 times 2.78 times the radius squared so that is 0.0139 kilogram meters squared. And then for body two, it's 1/2 times the mass of 1.78 times 0.08 squared so that is 0.0057. And so the total is I1 minus I2 because we're removing I2. And so that is 0.008204. Okay. And now, let me draw a free body diagram, and then everything is pretty self-explanatory from there, I think. Well, no, it's not. So step 3, hi. Step 3 is a free body diagram, and that looks like this. So here's our object. We have the weight force. We have the normal. We have a friction force here. Otherwise, it wouldn't roll. It would slide. Okay. And then you go to 4. You'll end up with more variables than equations by 1. And what you have to remember is, so you have to remember that we know that for rolling without slipping, A0 is equal to negative R alpha 0. And that gives you the one extra equation you need to solve this. But look at the PDF of the notes from Monday, and it sort of walks through all this stuff. Okay, that's all. Rocket problem Friday. That's a good example. So we'll.
So you are not joking?
No, we're gonna do it. That's a good example.
He just agreed to do number 15 before you were here.